All right, welcome back. So I'm going to do one more example here. Again, what we've been checking now is with our power series, right? We're trying to determine the radius of convergence. And then, of course, if we do have a non-zero radius, then we want to test the endpoints to see if it converges at the endpoints, because the test we're using, the ratio and the root test we're using, don't tell us what happens when it's actually equal to 1. So we need to be less than 1. So, uh, so let's go ahead now and take a look at one more example here. Here we're dealing with the series cosine raised to the k power of 2 over k x to the k. So we want to check the convergence of this as k goes from 1 onward, okay, to infinity. So since these are both powers, it would make sense to begin with the root test. So that's what we're going to do. In fact, I really don't know how we would approach this with the ratio test, with the trig function being raised to a power and stuff. Okay? So, with that in mind, let us consider the function here. So, limit as k goes to infinity of the kth root of this stuff. Now, that's going to be absolute value. Now, cosine can be negative, but as k gets relatively big, 2 over k is going to be very close to 0. So the cosine is actually going to be close to 0 on the positive side. So all the cosines as we go out to infinity are actually going to be positive. So I can actually write this just as cosine to the k, because I'm not really worried about those initial time or two that the cosine is actually negative. So we're not going to worry about that. X, of course, though, still needs to be inside absolute value. Okay. So we apply that, and we'll have limit as k goes to infinity of cosine of 2 over k. And then absolute value of x. And now we evaluate that, because as k goes to infinity, we know that 2 over k is going to go to 0. So we can distribute the limit through. That's going to 0. And cosine of 0 is 1. So cosine of 2 over k is going to go to 1. And so this would just be 1 times absolute value, would just be absolute value of x. And we know by the root test that for this to converge, that needs to be less than 1. That needs to be less than 1. So absolute value of x needs to be less than 1. Okay? And so that means our radius of convergence is 1. And so at this point, we're dealing with the interval that x has to be between 1 and negative 1. So what we don't know is whether or not we get to include the endpoints of 1 or negative 1. Whether we include one of them or both of them or neither of them. So what we have to do for that is look at the convergence of this series when x is 1. So, in other words, when x equals 1, we would have the series k goes from 1 to infinity of cosine to the k of 2 over k. And we have a couple of options here. We have a couple of options on how to approach this. We could try the root test. That's a very reasonable option to choose. All right. Unfortunately, if we do the root test and we did the root of that, cosine of the k, 2 over k. Right, that would be limit as k goes to infinity of just cosine of 2 over k. But cosine of 2 over k, as k goes to infinity, 2 over k is going to go to 0. Cosine of 0 is 1. And so, unfortunately, the root test is inconclusive here. Unfortunately, the root test is inconclusive. Okay. And as we already discussed, the ratio test probably is not going to be a good idea here. The ratio test is probably not going to be a good idea. That's probably going to lead to some problems as well. Okay, so with that in mind, what do? Well, what else do we have at our disposal? We know as k goes to infinity, cosine of 2 over k is approaching 1. What if we look at the underlying sequence here and see what it approaches? Does it also approach 1? Because it's being raised to the k power. So, and if you take 1 to the k power, right, that's going to be 1. But of course, if we look at it as k goes to infinity, this actually becomes a 1 to the infinity. But we can talk about that limit, at least see what happens with that. So the root test is inconclusive. So we look at just the underlying sequence itself. Does that approach 1? Because if it approaches 1, then that's not 0, and we know we'll have to diverge. So we compute that limit now. Limit as k goes to infinity of cosine to the k of 2 over k. And of course, that's a 1 to the infinity limit. So we would apply the logarithm. Limit as k goes to infinity. We apply logarithm. That'll be the exponent will come out. Ln of cosine to the k will come out. So we have k ln of cosine of 2 over k. And of course, that transforms this into a infinity times 0, because cosine is going to 1, ln of 1 is 0. So infinity times 0 limit. So we rewrite that as a division problem so that we can invoke L'Hopital's rule. So we take the top, ln of the cosine of 2 over k, divided by the reciprocal of the other one, 1 over k. And of course that gives us a 0 over 0 limit. So we differentiate. So limit as k goes to infinity. So it's going to be the derivative of the ln. So that'll be 1 over the cosine of 2 over k times the derivative of the cosine, which should be negative sine of 2 over k, times the derivative of 2 over k, which would be minus 2k to the minus second. And then on the bottom, we have the derivative of 1 over k, which would just be minus k to the minus second. Okay, so a bunch of stuff starts to clean up here now. The minus k to the minus second cancels out with one of the negative signs. And we end up with limit as k goes to infinity of minus 2 sine of 2 over k over cosine of 2 over k. So at this point, the denominator is no longer 0 or infinity, right? Because as k goes to infinity, cosine of 2 over k, as we've already discussed, is going to go to 1. So the denominator is approaching 1, so we can just evaluate this now. So, and k going to infinity is not a problem for sine, because 2 over k will go to 0, and sine of 0 is 0. So this is going to be minus 2 times 0 divided by 1 will be 0. So the limit of the ln goes to 0. That means the original limit now, the original limit goes to e to that power. So this thing approaches e to the 0, which is 1. And so since the limit of the underlying sequence approaches 1, which is not 0, then we know this thing is going to diverge. And that's by the divergence test. We know it's going to diverge. And in a similar manner, if we plug in -1 to give us what would be an alternating series, this stuff with -1 to the k, well, since the underlying sequence doesn't approach 0, we would also know that it diverges. That means it doesn't converge at 1 or -1, so therefore we know that the radius of convergence is 1, and the interval of convergence is just -1 to 1. So it will only converge between -1 and 1. Okay, so more difficult one here. This is one that actually shows that sometimes our better, more effective test, as we saw here, leads to an inconclusive result. But don't forget about our most basic test, our divergence test. Right here, the divergence test rescues us, where the root test just completely falls apart and is unable to work the problem out. Okay.